Welcome everyone to this lecture on the general concepts behind clustering. Keep in mind, we're not actually discussing any particular unsupervised machine learning algorithm for clustering. Instead, we're talking about the general concept of clustering. In the same way you can think of the general concept of regression or the general concept of classification. Clustering is an unsupervised learning concept where we're going to be working with unlabeled data. So as we mentioned, clustering uses unlabeled data and then looks for similarities between groups, that is clusters, in order to attempt to segment the data into separate clusters. So keep in mind, and this is something we're going to be repeating a lot, because the data is unlabeled, that is, it has no Y column signifying the correct class, then we don't actually know the true correct label for this data. And sometimes we can think of clustering as trying to discover this label. So let's imagine an example dataset we wish to cluster. Note here that we have feature x1, 2, 6, and so on, and feature x2, 4, 3, 2, and so on. Now notice again, we only have features. There's no Y column here telling us what class every single data row belongs to. But with only these features, we could attempt to cluster these. So how could we cluster this data together? A really simple idea would just be to plot this out and see if we can identify groupings. So if we plot this out, x1 versus x2, perhaps we discover the patterns. So here intuitively, I see two groupings. I can see the one towards the lower left and the other one towards the upper right. But keep in mind, I don't actually know for 100% fact that these are two separate groups. But you should notice that distance is kind of this intuitive metrics. And essentially what we're doing here is whatever the feature sets are, we're deciding that points that are closer together in this feature space are probably more likely to be similar than dissimilar, because the values of those features are closer to each other. And that's pretty much how every single clustering algorithm works. It takes a look at the points themselves on some sort of feature space and then decides, hey, these particular points seem to have similar features. They are probably going to belong to a similar cluster or a similar group. Which means you could then assign the clusters. And this is basically kind of discovering that Y label. But you should keep in mind, if you look at the original dataset, there was no original Y column. So you technically will never know if this is the right answer. Obviously, we're dealing with a very obvious example here, but it's not going to be so obvious for real-world datasets. So as I keep mentioning, we don't actually know for sure if this is a correct way of grouping together these data points, since there was no correct label to begin with. And what about situations that are not so obvious, or multidimensional? Here we are dealing with two features, so I can easily plot them. But we know that real datasets are going to have way more than two features, so I can't just visually plot them out when I'm dealing with 4, 5, 7, 25 features. So for example, take a look at this data. This is still quite simple, and it's just two features, so I could just plot it out. But now, it's much harder to tell what a reasonable number of clusters is. I could choose two clusters. So two clusters here is quite reasonable. I do see that there's kind of a set of points further away from this kind of bottom set of points. But maybe three clusters is also reasonable. There does seem to be some separation there. And again, there's kind of no way of truly knowing what the correct answer here is. There's no real ground truth, and we'll have to think about that. What is ground truth actually mean? So different methods can be used to actually decide on what the best number of clusters is. And when we talk about things like hierarchical clustering or k-means clustering, there's going to be trade-offs as far as how we decide how many clusters we're actually searching for. Some methods automatically decide on the number of clusters for you, and other methods have you, the user, decide first how many clusters you expect in the dataset. And keep in mind, clustering does not automatically label these for you. Even if you're super confident that there's three clusters here and that these clusters are correct, when you run this through an unsupervised learning algorithm, it's not going to spit back out the names or labels of the clusters. You're not going to see something like, hey, these are all the cats, these are all the dogs, and these are all the birds, because there's no real correct Y label. Instead, unsupervised learning is just going to label these group 0, group 1, group 2, with no real meaning behind those actual numbers, 0, 1, or 2. Instead, you, as the machine learning practitioner or data scientist, are then going to have to dive deeper into the data and see if you can figure out what a reasonable label is for these particular clusters. So no clustering unsupervised learning algorithm is going to be able to tell you the direct label that belongs to each cluster. That's up to the actual domain experience of the data scientist or machine learning practitioner to try their best to figure out. So we're going to try to go from something that looks like this to figuring out the maybe most reasonable or logical label like cats, dogs, birds. But we only get to work with this result. So what are the main clustering ideas here? The first one is we're using features to decide which points are most similar to other points. And intuitively, we can see that as some sort of distance metric in this feature space. Again, we have to realize that there is no final correct Y label to compare cluster results to. So if this is truly unsupervised learning, then we don't have a label, which means I can't actually do something like measure accuracy or root mean squared error on these particular clusters. However, we'll see later on that there are pretty clever ideas and metrics we can use to decide whether or not a unsupervised learning cluster result is reasonable. And really what we're going to do is think of clustering as an unsupervised learning process that discovers potential labels. So when we're shifting to unsupervised learning, we have this paradigm shift. And you should think about the questions. What about a new unlabeled data point? Recall that from supervised learning, we were always trying to predict the results for a new unlabeled data point. So how does this work when all your data was unlabeled to begin with? And would you assign it to a cluster? And how would you actually know what the correct cluster for assignment was when you don't even know if your original clusters were correct? So the question for something like how do we assign a new data point to a cluster is actually going to be a different approach depending on the unsupervised learning algorithm used. But at the end of the day, we would use features to assign the most appropriate cluster, again, based on some sort of distance metric in that feature space. And just as before, there's again no real way to measure if this was the correct assignment. Now, another really common question is, hey, if we've discovered these new cluster labels, could we use that as a Y for supervised training? And the answer is yes. In fact, this is actually a very common process for more advanced machine learning methods, where you have unlabeled datasets that only has features, and then you're able to use unsupervised learning to try to discover a reasonable cluster or grouping and treat that as your new Y. And then you set that loose on a supervised learning algorithm and try to go into something like classification. So that's where you're going to use unsupervised learning to discover possible labels, and then later on apply supervised learning on the new data points. Now there is a major trade-off here. And what is that trade-off? The major trade-off is that clustering in general with the unsupervised learning method didn't actually tell you what these new cluster labels represent. Recall, it's just telling you something like group 0, group 1, group 2. It's not actually telling you, hey, these are all the cats, these are all the dogs, these are all the birds, etc. And more importantly, there was never a real way of knowing if these clusters are truly significant or, more importantly, if they're truly correct. So some ideas on clustering that are still to come are questions like, how do we actually decide which number of clusters is the best? And do we decide or do we let the algorithm decide? And how can we measure this goodness of fit for clustering without a Y label for comparison? And that's really getting at the idea of there must be some way to understand a reasonable number of clusters or a reasonable choice for clustering versus things that are unreasonable. We know on those previous examples, it didn't make sense to choose something like 100 different clusters. We could see that 2 clusters or 3 clusters were reasonable, but 100 different clusters is probably not so much. There's probably a clever mechanism in order to decide on the number of clusters that are going to work for us. And then when it comes to unsupervised learning and clustering in general, this is where we start to discover machine learning is just as much an art as it is a science. And when we're thinking about art, we start actually getting into a little more of a philosophical understanding of machine learning. Because recall, we're actually discovering potential Y labels. And when we think of a Y label for a supervised learning, we're thinking about that as a ground truth. So the questions we should be thinking of is, what is ground truth? And what trade-offs are we making by using unsupervised learning as a substitute for ground truth of the Y label that was not given? And was there any way to actually ever know what that ground truth for any potential Y label was? So lots to think about. I want you to keep these ideas in mind as we discover the different algorithms behind clustering. Also keep in mind that it's much harder to compare unsupervised algorithms against each other due to the lack of ground truth-based performance metrics. For example, in supervised learning, we're able to compare two totally different classification algorithms against each other. We could compare logistic regression versus random forest classification because we could directly compare the accuracy results of each of those models. When it comes to unsupervised learning, there's a huge lack of those performance metrics, especially when we're trying to compare two completely different methods for performing something like clustering. So keep that in mind as we continue on. All right, let's go ahead and move on to understanding k-means clustering, which is a specific unsupervised learning algorithm for clustering unlabeled data. I'll see you at the next lecture.